Welcome back to ECE 207. Your homework number 3 is due today. Homework 4 is due on Thursday. This is Chapter 3 material for Homework 3. Chapter 4 is covered on Homework 4. Homework 5 will address Chapter 5 material, which is what we're talking about today and probably the next couple of days is Chapter 5 material, which we will begin today by defining RMS, root mean square, which we finished up with on the lecture that hopefully you watched before this class. We'll look at what the RMS value of a sinusoid is. I'll just give you that. It's actually in the book as far as the derivation. You should be able to follow that along. We'll then define phasors, look at combining phasors, and then go on to deriving complex impedances for inductors and capacitors. Why we're doing all of this is because we don't like to directly solve differential equations. Maybe you do. Homework 4 will sway you one way or the other. But those differential equations in Chapter 4, we're restricting our attention to one energy storage element, one capacitor, or one inductor. We would like to be able to analyze circuits that are a little bit more complicated than that. And when we are analyzing circuits a little more complicated than that, typically we're exciting those with a sinusoidal waveform. And if we're exciting a circuit with a sinusoidal waveform of a given frequency, omega in radians per second, we'll see that frequency all over in our linear circuit. It'll be the voltage, that voltage across the resistor will be operating at that same frequency. Because we are dealing with linear circuits, all of our currents and voltages will be oscillating or moving back and forth at that same sinusoidal frequency. Because of that, we can actually disguise our analysis or make it a little more direct or straightforward by putting the sines and cosines on the side of our paper and start analyzing with complex numbers. And complex numbers will allow us to do algebra instead of differential equations. That's the whole point of doing what we're doing today, is we're trying to abstract out this sines and cosines, push those to the side, work with complex numbers, and now we can use algebra to solve our circuits. We can write KVL, KCL with algebra relationships. Now the algebra is going to involve complex numbers, but that's okay. But that's why we want to get comfortable with working with complex numbers. We can add them, we can subtract them, we can combine them, we can divide, multiply. That's why we want to be able to do all of these different operations with complex numbers, and we will disguise those as these quantities called phasors. Phasors have it's not these guns. We won't be shooting off any, I don't know what phasors are, but I do know what these phasors are. How's that? So we'll use the phasors that have a magnitude and an angle. And if somebody says, oh, what's that phasor? You'll be able to see visually where that phasor is in the complex plane. If somebody says, oh, it's a magnitude 10 at an angle of 40 degrees, you now mentally can see that particular phasor. And we can communicate about phasors that way. Let's get started before I get going too off track with RMS quantities. The last time that we were together, which was when you were in your computer and I was in my office struggling to make this happen. If you saw the videos, you saw that one made my computer crash. Luckily, I turned off the microphone soon enough, and I don't think you heard anything that you shouldn't have heard. And then I continued, so there was a part A and a part B on the lecture that you were supposed to watch prior to today's. Let's look at, and when we finished that, we talked about RMS quantities relative to resistor voltages. The currents are similar. If we have the resistor current, let's say I sub r of t, which is periodic, and that periodic signal does not have to be a sine wave, but we will subsequently to this first piece typically specialize these currents and voltages to be sinusoidal. And when we do that, we can immediately go from the time domain waveform with a magnitude, a frequency, and an angle to its phasor representation, because we know the relationship between the time domain signal's amplitude and its RMS amplitude that we will use in the phasor notation. But if we just have a resistor that's being excited or driven by a sinusoidal waveform, then we could find the RMS current through that resistor by doing what it says, I sub RMS. We need to take the root, then we need to take the mean, that's just the average, and an average is you divide by the length of time, or one period over which you're averaging, and we can get an average by integrating. So there's the root, here's the mean, and we want to do that on the square of the waveform, and there's the S in the subscript. Meaning there's the RMS, or the root mean squared. You square, take the mean, take the square root, there's the RMS value of that periodic waveform. That periodic waveform obviously has a period of capital T units of time. If we now have the RMS value of the current going through that resistor, it's easy to compute the average power. Structurally now, that looks just like what you're used to seeing for DC type waveforms, which is I squared R. It's just now that I represents the RMS current value. We square that, multiply by R, and that gives us now the average power absorbed by that resistor. Meaning on the test, if I give you a periodic signal, I sub R of t, and say give me the RMS value of that, you should be able to compute that quantity. Whether that's a current, a voltage, I could make it something else, and I could say give me the RMS value of a arbitrary signal or waveform. And you should be able to compute it using that particular formula. You square the signal, take its mean value or its average, and then take the square root of that quantity. If we actually specialize that time domain waveform, I sub R of t, to be a sinusoid, we can then actually compute this for a generic sine wave and see the relationship between magnitude of this periodic waveform, I sub R of t, and its RMS value. The RMS value of a sinusoid. And when I say sinusoid, I'm meaning that in the generic sense, that means it could be either a sine wave or a cosine wave. This is discussed on page 203, which if you have a time domain signal, let's say V of t, that's a sine wave, a sinusoid, let's say it's a cosine with an amplitude of V sub m, a frequency of omega, and maybe it has an angle, an offset of theta degrees. If you go through the algebra to square that, take its average value over one period of time, what's the period of that waveform? What's the question?
Isn't theta, like that's the phase angle, isn't that usually phi?
The question is theta usually phi? I don't know. It probably depends on your textbook. Notationally, I'm going to call it theta. Does the textbook call it phi? If it does, I apologize, but hopefully you'll know by context that we're talking about its phase angle. So I'm not doing it to confuse you, but now I've probably really confused you when I said, oh, theta is phi. But it just depends on who's writing the book or the paper. But in this case, I've defined theta to be the phase angle. Theta is typically in degrees. Omega has units of radians per second. How many radians in a revolution? 2 pi. So 2 pi is equivalent to 360 degrees. You probably need that relationship to convert the units either from radians to degrees or degrees to radians, so that if you needed to compute that, to take the cosine, you don't want to be mixing radians and degrees. From omega, we can actually find the period, which this is sort of an aside, so I'll do that in blue. You'll know that, correct? The period, I always remember this relationship. Omega is 2 pi f, where f is in hertz, or cycles per second, and that's equal to 2 pi over t. Meaning, if you wanted to sketch this v of t, and you're given omega, if omega is 50, you can say, okay, what's my time axis look like? You can find what capital T is, and that will give you the length of time for one complete period of that waveform. And if you wanted to sketch 2 periods to give you a feel of what's going on, then you would sketch that for 2 times capital T, and this particular relationship will allow you to find what capital T is. That's 2 pi over omega. Questions on that? And if omega was 50, then capital T would be equal to 6 over 50. Well, that's kind of a weird number. So let's just say 6 over 48. I can kind of divide those out. That's 1/8, so that's 0.125. We're looking at roughly 125 milliseconds as far as the length of time for one cycle of this waveform, if it had an omega of 50 radians per second, if that makes any sense. So if you need to sketch this, you now know what you're looking at in terms of your axis. Where was I going with this? Oh, if you look in the book, or if you just do it, maybe you've already done it in the time that I've been spending discussing it, did you find the RMS magnitude for a cosine wave that had that particular magnitude? If you do, you'll square cosine, and what happens when you square cosine? A lot of times you'll represent that as 1/2 plus 1/2 cosine 2 omega, or 2x, whatever your argument is. Then cosine of 2x over one period goes to 0. Same amount of positive area as negative area under the waveform, and you really just have that 1/2 coming out. And we're taking the square root of that, meaning the RMS magnitude is going to actually be Vmax. Why did I change the subscript? Again, to confuse you. So now whenever I want to confuse you, I'll just say theta is equal to phi, right? And then you'll know what I'm meaning. Sorry. Now you're really lost. If somebody gives you a voltage with a magnitude V sub m, and you want to analyze this circuit using RMS and complex numbers, all you really have to do is say, oh, I'm going to convert everything to RMS values or units, and I can do that by just dividing the amplitude of my original cosine waveform by the square root of 2, and now I have my RMS value, magnitude. Likewise, if somebody gave you an a current expression, you could take the amplitude of that current, divide it by the square root of 2, and now you have the RMS magnitude of that current expression. question on how you can convert a time domain sine wave, sinusoid, into RMS values. Now that we have that, now we can talk about this idea that we call phasors. If we have a voltage that's an amplitude v sub 1 cosine omega t plus theta, oh, now we're going to get excited, because now I'm actually going to bar one of these. That's not a hat, that's not a tilde, that's a bar. That's now the RMS value. Or, I'm sorry, that's the phasor. Oh, I'm really getting confused. Theta is equal to phi. This is now the phasor. If I want to just say, here's a phasor, and I want to suppress the magnitude and the angle, I would just write v sub 1 bar. But that v sub 1 bar means a lot. It's meaning that that's now a magnitude and an angle. Is that making any sense? Now you can appreciate the question that was asked earlier, what do you mean by the bar? At that time, I didn't mean anything by the bar. It was just a different variable. Now it has a meaning. It now means that that has a magnitude and an angle. What you may want to keep in mind, though, is that that corresponds to a particular time domain signal, this guy, at a particular frequency, and we sort of maybe lose track of that, but you need to keep that in mind. And so you may want to keep this omega on the side. So when you're ordering a salad, you might want your dressing on the side. If you want a phasor, you keep your omega on the side. Sorry. So keep omega on the side. Not of your table, but on your paper. Is that clear? Because that omega is going to be valuable. That omega is going to be used to find the complex impedances for our inductors and capacitors later, if we can get that far today. There's the phasor form. The exponential form, does everybody remember Euler? Good. So Euler tells us what? I hear a lot of e to the i's. I don't use i's because i's will get confused with current, and you'll say, is I equal to j? Of course it is, but now I'm using it for a current, and you'll go, what? I'm confused. So I use j for the square root of minus 1. E to the j theta, that's this cosine. Oh, maybe I shouldn't have said theta. That's not phi. You guys are really hard on me here. How's that? So we're going to use that to represent an e to the jx you could actually think of as a rotating phasor. If you projected that rotating phasor onto the real axis, you would get the real part of that expression. That's cosine of x. Meaning, if I want to represent not a phasor, but if I want to write that in an exponential form, a time domain sinusoid, I could say in exponential form v sub 1 of t is actually the real part of v1 e to the j omega t plus theta 1. Is that consistent with what I had v sub 1 of before? V sub 1 of t was a magnitude of v sub 1 cosine omega of the argument omega t plus theta sub 1. If you now apply Euler to this, you'll get cosine x plus j sine x, where x is equal to omega t plus theta 1. You take the real part of that, and out comes v sub 1 of t. But what we'll be able to do is actually do our analysis inside the curly braces, and then at the end, if we need it, we could find the real part of that, and that's now what we have in terms of a voltage across an inductor or current through one of these devices, if we want it. We could also think of V1 of t in phasor form, and I would say that now if we do that, we're really sort of moving out of the time domain and into another domain. But now we have the barred, and this is now V1 at an angle of theta sub 1. Pictorially, you could think of that as a magnitude. What do I want to do this in? Let me go ahead and say that's in black. This magnitude or length is V1, and this angle is theta 1. And that would be this V1 bar, or the phasor of V sub 1. In the green axis, here's my real part, and here's my imaginary part, and that particular line, now you'll be hard-pressed to see what I just did on the videotape, but I'm making a circle with my finger, and it's going counterclockwise. This is spinning at an angular frequency of omega, and if you projected that down onto the real axis, that would give you the cosine of omega t plus theta 1, the actual value. If somebody said, oh, why don't you show me where v sub 2 of t is, where v sub 2 of t looks like that. V sub 2 of t is equal to 3 cosine omega t minus 30 degrees. Where would that go? If I had you sketch that on this complex plane with a real part and an imaginary part. It has the same omega, so we can sort of think of these as the same. Or being viewed similarly. They're spinning at the same rate around the origin. I didn't give you a value for v sub 1. Is that why you're getting uncomfortable? You don't know the length of that vector? How big is this v sub 2 vector? 3. And now, since I really didn't give you what v1 was in a length, let me just say, okay, here's basically 3. Whoops. I maybe didn't do too bad. Is that about 30 degrees? This is supposed to be 30 degrees, and it's relative to the positive real axis. It's now this minus 30 degrees. And this length is 3, meaning this particular vector is v sub 2, or phasor, which has a magnitude of v sub 2 at an angle of minus 30 degrees. They're spinning in the counterclockwise direction, and because they're both spinning at the same frequency omega, they aren't going to change in terms of their relative orientation with each other. And in this case, we would say that v sub 1 leads v sub 2 if we wanted to talk about their relative relationship to one another. Question?
What do you mean they're spinning?
What do I mean by they're spinning? If I could get 3 volunteers, I would have you come up and spin. So I just mean this. Ooh. And they're doing it counterclockwise, and they're spinning at a rate of omega.
If they're going around?
It's just spin. So if you wanted to think of what this V sub 1 of t was doing, if you view that V sub 1 of t as a vector with amplitude or magnitude V1, so there's a line, and now it spins at a value of omega. If I said, oh, it's spinning, omega, let's say, is 2 pi radians per second. So every second it would spin 1 revolution, 6.28 radians. It's going around and around. Now, relative to taking a snapshot, t equals 0 says, oh, we're actually offset by theta 1. At t equals 0, whatever they've decided that is, now in 2 pi radians, boom, it's back there. It's back there. So if you had a strobe light that was operating or taking a picture or a snapshot, you would always see this vector at an angle of theta 1 if that strobe was at the frequency omega equal to 2 pi, for example. So that's roughly a little more than 6. If your frequency omega is bigger than 6, obviously you're spinning much faster. We're not worried so much about it spinning. We're just wanting it to understand where we are relative to all the other vectors in the circuit. We know they're all spinning. They're all oscillating at omega. We now want to know how are they oriented or related one to the other. And so if the current is lagging the voltage, we know what that means. It's now behind it. Or if the current is leading the voltage, we now know what that means. Questions?
Are they spinning in the same direction?
Are they spinning in the same direction? Yes, they are. They're all going to be spinning in this counterclockwise direction. And in this case, V sub 2 had a frequency of omega. V sub 1 had that same frequency. You could have two different frequencies going, and then they might start passing each other, and we'd have NASCAR on your paper. Sorry. Question? Yes?
So basically it's just another way to analyze, say, the sinusoidal graph of voltage.
Yes, the question was, it's just another way of visualizing or thinking about. It's actually going to be a easier way to keep track of sines and cosines when we're solving differential equations. We're actually going to run around here and go over here into the frequency domain and analyze with algebra instead of having to do chapter 4 problems and always working with derivatives and differential equations. So all of this machinery is going to help us simplify our analysis. We'll just be doing algebra instead of Diffie-Q. That's why we're wanting to convert all of these time domain signals into phasors. Questions? All right. You're experts, so take out a piece of paper. It's only going to take you half a semester to learn what these code numbers are. That code number is to give you credit for doing these exercises. I'm getting these people going, I have no idea what my code number is. Wow, that's a little late. If you don't know what your code number is, that's what I wanted you to put on your test so I could start giving you credit for all these class participation problems. Tell me what your code number is and give me your name if you haven't done that before. If you've been consistent and know what your code number is, put that on your paper. It's much easier if everybody has a code number, then I only have to enter it once and I don't have to flip-flop between Excel spreadsheets. Who's number 685? Some of you do have the same code number, and now I've forgotten which ones those are, so put your initials next to your code number. It's really secret. It's very anonymous now. But here's what I want you to do. First part, I want you to express a couple of these in phasor form. You don't have to write this down necessarily, but I want you, well, you could in your notes and then hand in your answer basically. But if you now have V sub 1 of t equaling 8 cosine of 100 pi t plus 10 degrees, and that's, let's say, a voltage, V. Let's say another one is I sub 1 of t. That's why we don't use I, because now I have I, and you don't have to think that that's the square root of minus 1. That's now a current. I sub 1 of t, let's say, is 6 sine of 300 pi t plus 30 degrees, and that's a current. Let's say that we now have v sub 2 of t equaling 10 cosine of 300 pi t minus 45 degrees, and that's in volts. That's part A. Part B, so now just give me the phasor forms of A, B, and C, parts A, B, and C. Part B is answer the following question. Does I sub 1 of t lead, bless you, or lag v sub 2 of t? And hopefully it's clear what I mean by lead or lag. So does I sub 1 of t lead v sub 2 of t? So I guess don't answer that with a yes or no. Say it's either leading or lagging. It's either in front of or behind, basically. Okay? You should be done. Turn them in. All right, 2 minutes. Did everyone get the answer to this? And does it make sense if I ask you about leading or lagging of V1 with respect to V2 or V1 with respect to I1? Would it make sense if I ask you a question about leading and lagging with those? No. Why? They're at different frequencies, aren't they? So they're spinning around this track at different rates, and it's not really fair to start comparing them in terms of leading or lagging. But I sub 1 and V sub 2 are spinning, rotating at the same frequency. So we can talk about those relative to one another. Question? I'm sorry?
They're like opposite of one another. Like,
So what if they're 180 degrees apart?
yeah.
Good question. Pick a number, any number. Actually, you could say whatever you wanted, probably. You could say they're out of phase. One's exactly the opposite of the other, in a sense. So if they are 180 degrees apart, You could say, oh, it leads by 180 degrees or it lags by 180 degrees. It's sort of however you want to interpret it. But in this case, how do we convert V1, or what did you get for part A of A? The phasor of V sub 1. Magnitude of 8, an angle of 10 degrees, and on the side is omega equal 100 pi. Ooh. No, I didn't say you had to write that. But you'll only get 1 point out of 20 if you didn't. No, but you need to keep track of that omega. You needed that if you were now comparing different frequencies. And somebody said, oh, is one leading or lagging? And you go, it doesn't make sense. They're spinning at different rates. But the other two parts, B and C,
If you said they were leading and sorry, if you said they were leading and lagging within a certain time interval, then can we answer that question?
the question was if I ask you about a particular time interval. You're getting nervous with those papers, aren't you?
No, I'm good.
Sorry. No, really you don't even want to go there in terms of time interval. You could say a snapshot. Somebody could give you a snapshot maybe in time and say, oh, which vector is leading or which one is lagging. But in a sense, it's never, they're spinning, and if they're at different rates, they're going to catch up or slow down, and that particular separation won't really occur except every so often if they're integer multiples of each other. So it's really not a valid question to ask or to say one's leading or lagging if they're spinning at different frequencies. So I wouldn't even get too concerned with that particular issue. I would just say they're spinning or they have different frequencies. And will that happen in a linear circuit? It won't unless you have multiple sources, and those sources are operating at different frequencies. But you could use superposition, couldn't you? You could kill one source that's going at 60 hertz and analyze the circuit that's left. Maybe you have a European source and it's going at 50 hertz. You could solve the circuit for that source that's maybe at 50 and another source that's at 60. You could kill the 50 and analyze the 60. Now you put them together if you need to look at the combination, and you could at the end. Well, that's one reason why we looked at superposition. All right, what's I sub 1? I sub 1 was sort of a curve, wasn't it? Because I gave that to you in terms of a sine, and I gave V sub 2 in terms of a cosine. You really need to convert one to the other. In this class, let's just try to keep everything in terms of cosines. Once you've converted those to cosines, now you can compare their relative spacing. You can't necessarily say, oh, I1 is 6 at 30 degrees and V2 is 10 at minus 45. That's not quite right, because one is a sine wave and one is a cosine wave. Meaning, let's convert everything to cosines. Well, that doesn't change the magnitude, does it? So the amplitude would be okay. Maybe I'd give you 1 out of 20 for getting that right. But I'm hard on partial credit, aren't I? Yeah, I knew you would agree on that. When we switch between sine and cosine, we're not changing omega, are we? All we're doing is changing it by how much? How is cosine related to sine? They're 90 degrees or pi over 2 different. And in particular, if we take 90 away from the cosine, we're back to the sine. So now this is equivalent to that sine wave of 300 pi t plus 30 degrees. We now have cosine of 300 pi t minus 60 degrees. Or we now have a phasor of 6 at minus 60 degrees. And that one we can compare with V sub 2 as a phasor in terms of its cosine. So that now C, which was V sub 2, whoops, I don't need to go in the time domain. Let me just express it as a phasor directly. And now I have V sub 2 is 10 at an angle of minus 45 degrees. And that's in volts. Now we should be able to compare B and C relative to each other. They were both at the same frequency, 300 pi. They're both spinning at the same rate. So if they're offset in angle, they maintain that offset because they're spinning at the same rate. If you wanted to get a picture of this, which I like, I'm visual. So here's my complex plane. I could draw V sub 2, which would be 10 at minus 45. That should split those two right in half, which I'm not sure it does, but yours can be more accurate. You might want to bring your protractors to the next exam and your dividers, and everybody goes, dividers? Never mind. This is now my angle of minus 45 degrees. This is a length of 10 if this represents V sub 2. Where is I sub 1? Relative to that, it's 60% of that length. I'm not sure I'm going to be able to draw that, but there it is. And that's supposed to be at minus 60 degrees. Here's I sub 1, and that's at an angle, or a value of 6. In this case, I sub 1 lags V sub 2, and I should get rid of that dot. I sub 1 is behind, or V sub 2 leads I sub 1. You can say it many different ways. Questions on that? Is that what you got? Now you're shuffling your papers back in the other direction, correcting them and shifting them back. So that would be periodic if we did that. What would be the period of that? Did any? 9 minutes actually. Took a question. When I subtracted the 90 degrees, could I have added it? Is that what you're asking? Can anybody answer that? Does anybody remember their trig? No. Did anybody learn their trig? The short answer is no. You need to subtract. And the reason is, suppose that I now have cosine of x minus 90 degrees. Does anybody remember what the cosine of a difference of two angles is equal to? Not quite. It's that, isn't it? Cosine x cos.
That's what he said.
Oh, is that what he said? I'm sorry. I can't hear. So, what's cosine of 90 degrees? Oh, he started with sine, and that threw me off, didn't he? I'm used to starting with the cosine. And what is that? That's why we did what we did. And if you put cosine of x plus 90 degrees, this would be minus sine x, and you would actually have flipped it by 180 degrees, or negated it. Does that answer your question? So that's the difference between, or that's how we convert between sines and cosines. If you're given a sine, subtract 90 degrees from the argument, and now you've got cosine, and you can start comparing them relative to each other. Great. So now that we are experts at combining phasors, meaning if I said, oh, I have v of t equal to 5 cosine of 8t plus 40 degrees minus 4 sine of 8t plus 10 cosine of 8t minus 30 degrees. Or that's now v of t is a combination of v1, v2, and v sub 3. And I could have three different voltage sources, V1, V2, V3, stacked on top of each other and exciting my circuit with those three voltages. Or somebody said, that's making my head hurt. Can you just give me one? Can you? Can you collapse that down to one source? Why did you answer yes? They're all at the same frequency. Since they're all at the same frequency, we can combine those into one. Pardon? Oh, man. I wouldn't have said combining phasors. I wouldn't have put a 6. You guys are sharp today. I'm still asleep, and you guys are killing me here. There's my 8. So I wouldn't have led you down this path you're saying if it wasn't possible. All right. So if we want to combine these, how do we do it? First, okay, we could convert to phasor form. We could do it exponentially. I'm going to do it both ways, and then hopefully you'll feel comfortable just going immediately to phasor form, which is the quick way, and working it. But we'll do it both ways. The first thing that somebody suggested is let's get them on an even playing field. And that means we need to convert this sine to a cosine. And we just learned how that can be done. We can take sine of 8t, and that's equivalent to cosine of 8t minus 90 degrees. Isn't that what we just showed? Now we can start combining those. And a lot of times it helps me to actually sketch those so that I can see vectorially what's going to happen. V1, in terms of how I had defined it, V1 was the first one. That was a magnitude of 5 at an angle of 40 degrees. So I might say, well, here's 40 degrees and there's a magnitude of 5. Then the next one, V sub 2, is minus 90 degrees, but I was actually subtracting that. So that now flips at 180 degrees. And it has a magnitude of 4. What was this? A magnitude of 5. So now I would be down here, but I'm flipping it so that I'm now up here, and that's now 90 degrees. That's because I was subtracting. So whenever I subtract, I'm basically turning around and going the other direction. Because I was now subtracting 4, I would have minus 4 cosine of minus 90. That could just be the same as 4 cosine of 90, which is the V sub 2 right here. And that's supposed to be of length 4. Hopefully this is somewhat accurate. That looks almost longer than the 5, but it's not supposed to be. And then I have V sub 3, which is of length 10 at an angle of minus 30 degrees. And this is now my V1, V2, V3, and V2. I could put those head to tail, and wherever I end up with, that's actually my resultant, or the combination of those. And let's see where that actually takes us, and we'll do that with representing these in exponential form. Question? It was negative 90, wasn't it? The question, so I kind of did 2 or 3 things at once. We replaced the minus 4 sine of 8t with minus 4 cosine 8t minus 90, but since we are subtracting it, I basically said, oh, if we're subtracting, we're really flipping that vector 180 degrees, and that's why we came around and said, oh, it's actually at 90 degrees, a plus 90 degrees. Let's now do that with exponential notation. V of t is the real part of 5e to the j 8t plus 40 degrees minus 4e to the j 8t minus 90 degrees. I kept the minus sign there. Plus 10e to the j 8t minus 30 degrees. That's the v of t that I had written before, except now I'm writing it as exponentials, and I'm just taking the real part of that. And if I did that term by term, I would have the v of t that I had written down before, these cosines. Questions on that? Now just use your knowledge of algebra and exponents, meaning that e to the j8t, that's telling me how fast it's spinning. That's common to all three terms. Let me just get rid of it. Or I'm sorry, let me factor it out. I'm not going to get rid of it, but let me factor it out, and then I can play with what's left. I now can say, okay, well that's the same as the real part of 5e to the j 40 degrees minus 4e to the j minus 90 degrees plus 10 e to the j minus 30 degrees, all times that same spin, e to the j 8t, and that's just factoring out that spinning exponential. I can now use Euler on all of those e to the j's inside the parentheses, meaning this is now the real part of 5 times cosine 40 degrees plus j sine 40 degrees. I'm now expanding inside this real operator because I need to try to combine these vectors. One vector is 5 at 40 degrees, another is minus 4 at minus 90, and another is 10 at minus 30. And I'm going to do that by converting those exponentials, complex exponentials, to their rectangular form, cosines and sines. Then I have minus 4 cosine of minus 90 degrees plus j sine of minus 90 degrees. And I could have done that in the other way. I could have said, oh, let me just consider that to be cosine x minus j sine x. It's the same thing that I've written down, plus the 10 times cosine of minus 30 degrees plus j sine of minus 30 degrees. All of that's e to the j 8t, and I want to take the real part of that at the very end to get back what I wanted, my combination of those three spinning phasors. Now I simply need to take those sines and cosines, convert those into numbers, keep the real parts together, or combine those with the imaginary parts, and that now will give me a complex number that I can then turn into an exponential again and combine it and then pull it all out at the end. Meaning, I now have the real part of 5 times cosine of 40 degrees, that's 3.830. The sine of 40 degrees, oh, I've already done my combination. So let me go ahead and combine the real parts. What's the 4 cosine of minus 90? 0, so I don't have any of that. And then I have 10 times cosine of minus 30. Cosine of minus x is cosine of x. Cosine's an even function. Cosine of 30 degrees is at the 0.866. So I now multiply that by 10, and I have 8.66 there. And now I can put all of my complex pieces together. 5 times the sine of 40 degrees, 3.214. Minus 4 times sine of minus 90. Sine of minus x is minus sine of x. Sine of 90 is 1. I've negated that, so I now have plus 4. Sine of 30 degrees.
Wait, sine of negative.
Yes, sine of negative 30 is minus sine of 30. So let's do sine of 30. Sine of 30 is 1/2. I need to take care of the negative sign, and I now have minus 10 times 1/2, or that's now minus 5. And all of this is still spun at e to the j8t. Does everybody see what I'm doing? I'm stepping this through with all the steps so that you feel comfortable with what we've done, and then you'll say, oh, let me just do it in phasor form. This is now the real part of 12.49, hopefully my algebra is correct, plus j, whoops, wish I'd quit making mistakes because I hate to erase it. It's painful. 12.49 plus j 2.214 e to the j8t. Now we can turn that rectangular number into its polar form by its magnitude as the real part squared plus the imaginary part squared, square rooted. That's not going to be much bigger than what the real part is because of their difference, but it's now 12.685. What's the angle? In terms of a formula, how would you find that angle? Can you see where we are vectorially? We're 12.49 in the real direction. Arctan of the imaginary part over the real part. And that ends up being 10 degrees roughly, 10.05 degrees, e to the j8t. But we want to convert that complex or polar form into a magnitude and an angle so that the angle can go up into the e to the j part. We'll turn that back into an exponential so that we now have 12.685 e to the j 8t plus 10.05 degrees. And if we take the real part of that, we now see that v of t is actually 12.685 in magnitude cosine 8t plus 10.05 degrees. And that's now the combination of those three voltages that started out at, I don't even remember what they started out at, 5, minus 4, and 10, with one of them actually being a sine. How did I get the 10.5? So if we were going, I would just draw this sketch, and I'm working from this complex number. I want to convert that into a magnitude and an angle. And if I do that, down here, that's 12.49 in the real direction and 2.4, so I would walk over here to 12.49, and I would go up, whatever I just said, 2.2, so that if I had to find this, and hopefully your sketches will be little bit better than this. But now this angle, the length of this vector, ouch, that's pretty bad. That length should be the 12.685 that we had. And this angle right there is the 10.05 degrees, which is this inverse tangent of 2.214 over the 12.49. That's how I obtained the 10 degrees. And this radius, so what's that frequency of that vector? I better turn off the microphone. All right. Now I have 0 is equal to the inverse tangent. But that's a phi if you couldn't tell. Sorry. It was a theta, I promise. All right. So theta, which is this guy, and this was supposed to be r, but it kind of got lost in that last vector. R is now equal to the square root of the real part squared plus the imaginary part squared. And you should get very comfortable doing that algebra. Questions on that? Question?
Do we have to carry through with exact numbers, or can we round to like 3 decimal places?
Oh, the question was, can we round? What kind of accuracy do we need? Wow. Didn't you get that in Engineering 102?
Well, I mean,
Significant digits. I rounded. I'm pretty sloppy up here, but don't do what I do. Do what I say. Okay? I was sketching. That's why I rounded to 2.2. But if you're actually computing this, so if you're sketching, I mean, my sketches are not even going to be accurate to 1 decimal, let alone 3.
Like in your work, like you had a value for cosine of 40 degrees, which is not exact, and then moved on.
Man, I told you guys were hard today on me. Use what your calculator gives you in the intermediate steps and then round at the end. Does that make sense? So if you start with a 5 and you take the cosine of 40 degrees, I would use whatever your calculator is giving you. I'm trying not to give you 8 significant digits or 10 here because I'm already getting writer's cramp. Okay? Other questions? Yes?
So pretty much what we're doing is taking 3 different vectors and adding them, and then using the resultant vector and finding the theta of that magnitude of the resultant. Is that true?
Yes. Did everyone hear that? We started with 3 vectors that are spinning at the same frequency, which was 8, I believe. And that was 8 radians per second. So if you were actually thinking of this, it's going a little bit more than 1 revolution every second. 6.28 would be 1. So now it's going 8 radians per second. A little bit more than 1 is how fast it's spinning. And we were able to combine those or convert those all to their exponential form, combine those up, and now we've put all of those sines and cosines instead of doing trigonometry. We could have done all of this with trig, but we did it now vectorially. Let's do it in the phasor form or in the quicker version. And what we're trying to do is get comfortable with this process or concept so that we can do this rather quickly and we can do the algebra instead of having to worry about derivatives or these differential equations with sines and cosines, because that gets kind of tedious, trying to solve differential equations with cosine and sine forcing functions. Now we can just put them into the phasor form, do our algebra with complex numbers, and if we want, we can pull those back into the time domain at the very end. Is that making any sense? So now instead of using superposition and solving this silly circuit 3 times, we do this preliminary work, combine all of those sources into one. Now we just have to solve the problem once, if we needed to, with that one source. V1 as a vector was 5 at 40 degrees. V2, we needed to convert that to a cosine, which was minus 4 at minus 90 degrees. But with algebra, we can always multiply that by 1, can't we? And not change anything. And my 1 looks like that. Does that look like 1 to you? Yes, no? That is 1. Meaning, if you look at this, I'm saying, oh, everything is relative to this positive real axis. If I say minus 1, I'm over here. But now that's at an angle of 180 degrees. So spin that around 180 degrees, and now you're back over here at 1. So I'm multiplying by 1, which is okay. That says minus 1 times minus 4 gives me 4. I can add my angles, minus 90 and 180, and now I'm at 4 at 90, and that's what we'd already done before. We'd convinced ourselves that that same minus 4 at minus 90 was equivalent to 4 at 90 degrees. But that's now V sub 2, phasor form. V sub 3 was 10 at minus 30 degrees. Bless you. If we now want the sum of those 3 phasors, we don't have to carry through all of that hardware in the exponential form. We can just work in phasor form. Meaning, now that we have these as phasors, view that as a vector of 5 at 40 degrees. And you can break that into its real component and its imaginary component. Meaning, when we've already done that, but that was 3.830 plus J 3.214. V2 was 4 at 90 degrees. That's actually all of that 4 is in the vertical direction or dimension, so it's J4. And finally, V3 was 8.66 minus J5. And you could sketch those in the complex S-plane and see if that seems to make sense. V1, yeah, that looks like it's 5 at 40 degrees. J4, that's in the vertical direction at a magnitude of 4. And I go 8.66 and then down minus 5, yeah, that looks like it's minus 30 degrees at an amplitude of 10. Now I just add up the real parts and the imaginary parts. And do what I just did, convert that to polar form. Now that I have that polar number, oh, well, that just gives me the magnitude and phase of my cosine, and my cosine I know because I had it on the side. What did I have on the side? Your dressing, your omega. So now, this pretty dry, isn't it? So you're going to need a lot of dressing when you're working these problems. Questions on that? Is everybody comfortable with doing phasors? And it allows you to go from the time domain into the frequency domain. You may not have to go that far if you're working the problem, but you'll want to make that mental shift, right? But you know the relationship now. And the reason we're going into the frequency domain is to allow us to work these problems with algebra instead of with differential equations. Let's look quickly at complex impedances. I told you I would let you go a little early so you could make that lecture at 6. So we still have another hour to go. Okay? Complex impedances. Why are we wanting to do this? Because we want to basically get rid of Eli for a while. V is equal to L di dt. We would like to forget, or not forget, but we would like to not have to deal with derivatives all the time and just multiply by complex numbers or divide by complex numbers. Just do some algebra. Suppose I'm working with an inductor and somebody says, oh, well, let's say that that inductor current is I sub L of t, a magnitude of I sub m sine of omega t plus theta. That's the current. What's the voltage of that inductor? This is chapter 3. This is what should be in this pile. Eli, right? L times the derivative of that current. You're testing my patience. Somebody said we'd forgotten it. Well, that's not what I meant. So don't forget it, please. Remember it until you pass the PE exam. Eli, okay? That's now L di sub L of t dt. Or I guess it's the FE exam, and if you need to, then you'll take your PE after that. But probably if you're not an electrical and computer engineer, you just need it for the FE exam. The PE exam will be in your specialty, which may not be electrical and computer. But after this class, you're all going to convert, right? You've now seen the light. Yeah, you'll all come into electrical and computer engineering. All right, this is what we use. What happens when I differentiate that I sub L in the time domain? Impress your math teachers. Derivative of sine is cosine, isn't it? And then we differentiate the argument. So that omega jumps outside. The theta doesn't do anything for us. That's just a constant inside the argument, and it's not changing with time. Meaning, we now have L, I sub m we keep, and we now have omega cosine omega t plus theta. Okay? So we now can say that V sub L of t is omega L I sub m cosine omega t plus theta. If I wanted to relate these or compare these in phasor form, how would I write the phasor version of I sub L? How would I write that? And you might actually have to write it on the exam. So I'm not always going to be writing it. I needed to come up this aisle because my other leg was getting sore. What? It's I is a sign, isn't it? I'm going to fall down one of these days, and you guys will just sit there and laugh. Wasn't that funny? I sub L is a sine, V sub L is a cosine. We need to get them consistent. Let's convert to cosines. If that's the case, what does I sub L look like as a phasor? That's the easy part, isn't it? The magnitude. Then we have theta minus 90 degrees. And now you know why we subtract 90, correct? What's V sub L as a phasor? omega L I sub m right? What we'll do next time is we're going to now say, well, how are these related? Well, if we generalize this idea of resistance to impedance, we now want to say V is equal to ZI. We want to define the Z. So we'll figure out what Z equals for this inductor and a capacitor, and now we'll be able to play with our algebra.